选的是上面，
对，
这样。
好，那我们开始上课。好，那讲一下 logistics，OK，今天会把 LM 其实上次就大致上讲完，今天会在一些小细节把它调整完。那今天可能就也不会上这么久吧，因为上完了。那下礼拜就是这礼拜的下一堂课，我会讲一些deep learning base 的方法。OK， 那也是很快的 overview 啊。那比较是跟大家讲说，在这个 HMM GMM 的框架之下，那后来有人把它衍生成这个 deep learning 的框架。OK， 大家大致上是怎么做 ？OK， 那如果时间上允许，或许会一路很快带到最新的 state of the art， 我可以跟大家讲一下，其实它的逻辑大致上没有换的太多。OK， 只是我们在很多的 component 上面，我们用一些 neural network 的模型去把它换掉。那也会如果有时间，我跟大家稍微分享看一下 end-to-end 的模型啊。OK， 那大家如果知道现在的这个 HMM 模型，它其实有好几块 component， 它是拆开来的。OK， 我要一个字典。OK， 我要一个生选模型，我要一个语言模型。OK， 全部都是拆开来做。那拆开来做完就把它放在一起，变成一个语言辨识模型。那当然后期也有人觉得这样做法比较没有总体最佳解。OK， 所以在neural network机制下，它一定让它变成总体最佳解。但是大致上的概念不会差太多。OK， 所以我会很快的稍微讲到当然那堂课可能不是真的没办法完全 cover 到所有的 state of the art。OK， 那我是去年有开啊，但我忘记我想明年应该不一定会开，有可能会开。OK， 就是这堂课的下一堂。OK，advanced topic in speech technology。OK， 那边会就是教大家真的 state of the art。OK， 然后不从 ground up 做，就是 ASR 也做 ，voice conversion， 然后语音转换也做，然后speech enhancement denoising。OK， 这个我们做 speech 好多种模型。OK， 那就是直接带大家做 state of the art。OK， 只是说希望大家先有这堂课的基础，再去看下一堂课，可能会看得快一点。OK， 因为很多东西我们就是跳过，不会再教了那样子。下一堂课就会是假设HMM 一定是你大家完全了解，有可能是一页就带过了，那马上会进入到各种 state of the art。OK， 应该是忘记我好像下期有开这堂课，所以如果大家有兴趣，可以在上那堂实作就会再更多。OK， 那实作可能还没有很多。好，那再来是下一个礼拜就会有 lab。OK， 那一样是 Kelly 这个 tool， 那TA 会带来，基本上让大家慢慢开始做一些这个语音辨识怎么跑。OK， 然后拿自己的声音去做辨识，看看结果长什么样子。OK， 应该会有个比较初步的感觉啦，说到底这事情难度在哪边啊？资料的收集啊，资料的不足啊，然后怎么跑一些模型、一些参数这样子。好，那 lab 完之后，再下个礼拜就是 final 了。OK， final 就跟 midterm 有点像。OK， 智力测验。照理说，我们都一直觉得，照理说有在好好做 homework 哦，那应该大家上有办法 cover。OK， 不过我们如果计划，我们还是做点简单的 review 那样子。那final 会 cover 整堂课，当然有点 emphasis 会在后面一点，因为后面一点还没考过。OK， 比较是不是 DSP 的部分，而是比较几率然后统计跟这个训练的部分。OK， 尤其 Git model 是一个非常经典的模型，我希望大家真的很懂它。OK， 所以一些这种模型应该很熟。OK， 好，那基本上我们的 final 大概会还是有什么策略这样子，那会 cover 到 material up to today 啊。OK， 所以我们下一堂课教的那些 advanced model， 当然自然就是比较给大家的一个 general knowledge， 会在 final 里面。OK， 所以讲一下接下来这几堂课会发生的事情这样子。OK， 那我们就 go back to language model。So again, we'll talk a little bit about the evaluation. We'll talk a little bit very brief intro to information theory. Okay, so we covered this mostly because in automatic speech recognition system we require that language model as part of our decoding pipeline. Okay, so but processing language itself, using some statistical model to process language for various tasks, like translation, summarization, all sorts NLP tasks. Okay, it often treats this language as a set of symbols. Okay, and the math behind this. Okay, largely a lot of those are based on information theory. If you haven't taken information theory, if you're interested in sort of natural language processing kind of a tool, and mathematics are around, that's basically built upon information theory. Okay, information theory is built upon probability. Okay, so these are kind of the concept. We'll do a little bit of that today. Okay, but anyway, so language model is part of the ASR pipeline where basically as we decode using vectorial decoding, we need to find the maximum probability of word at every frame. Okay, so we need to know where we come from. Okay, the where we come from, it could be the same word just switching state, or it could be a different word. Okay, that different word coming from other word last state to the current word this state. Okay, that probability can be modulated by how likely that particular word sequence transition is going to occur. Okay, so that's basically the idea behind language model. Okay, and one particular realization of the language model is called n-gram language models. We talk about that side. You simplify the joint distributions of the entire word sequence by making a first order or second order Markov assumption. So the current word, the entire joint distribution only can be factored into probability of the current word given a past word or past two words. Okay, we call that either bigram or trigram. Okay, that's a simplification of a language model. Okay, and that language model is supposed to provide the probability of this particular word given the past word sequence. That probability is going to insert to the vectorial decoding as we decode through the entire ASR system. Okay, just keep this logic in mind, and we're really at the sort of that bottom. Okay, what language model do we use? And then we use n-gram. And we last time talked about the n-gram language model. But what you do is basically go out and collect text, right? The word corpus, okay, newspaper, anything, okay, and then you just do a simple counting, a particular count of some set of word happening divided by, bigram would be two words happening together divided by one word happening. Okay, use that count as the probability estimate. Okay, then you hit the problem with the sort of a zero count issue. Okay, so talk about various discounting issue, discounting problem. Okay. Back off and those things, sort of things, those heuristics, trying to readjust the probability estimate of a zero count probability to some very small amount of probability, okay? So that you make sure, okay, your model doesn't hit this sparsity problem. Okay, so that's the overall framing, okay, of the entire natural language model for ASR. So in the evaluation, we'll talk again, right? So you train your parameters on the training set, usually some large corpus. Repeat, it doesn't have to come from the same corpus where you have the speech data. Okay? The language model can come from any other text data. Okay? It could be from newspaper, it could be from Wikipedia, it can be from PPT. Okay, everything. Okay, so things you can gather text data gives you a sense of this probabilistic estimates of occurrences of words. Okay. So any text data you can get, usually you can get quite a bit of data. You can use that to estimate n-gram probability. Okay. So anyway, so you can evaluate how well our model works. You can model performance on some new data. Basically, that's how we usually do a recognition experiment. Happens in the real world, want to know how our model performs on data we haven't seen. So test set is the data that we're seeing. Okay, you need an evaluation metric to tell us how our model is doing on the test set. And the perplexity is a good metric for n-gram language model. It's not just good for n-gram language model, it's good for language model. Okay, if you look at even the current days, where when they release text large language model, they will tell you the perplexity of those language models. Okay, language model, this perplexity metric is just a measure of how well your model fits a particular testing set data on average. Okay, so we know n-gram model is the model that people use in ASR. Best evaluation for an n-gram model is just to put that model in per se. You have two models, put a model in speech recognizer, run recognition, get word array, put model B in speech recognition, get model B. We call this in-vivo evaluation. Okay, which is okay but very difficult. Okay, very time consuming. Okay, just running a simple experiment. Okay, it can take days to run an experiment. Okay, so imagine you have 100, 200 hours of data. Okay, just simply inserting a new language model into a decoding process takes a very long time, and you are only evaluate one number out of it. So it's a very time-consuming process of evaluating whether my language model is correct or not. So to evaluate n-gram language model, we sometimes use an approximation called complexity. That's a good measure if your testing data is like training data. But if your test data is not like training data, then of course your complexity is not very good. So it's only generally useful for a pilot experiment. If you're in a space of publishing for speech recognition systems, academic research, usually they will still require to actually run to a word array. If you are actually a commercial system, you also want to run that eventually to the speech recognizer to actually get the word array. But if you have 5 or 6 different parameters, 5 or 6 different small models, small tweaks you want to try on a language model, you don't want to do that every time to run an entire speech recognizer. But it's important to say, let's use those metrics as a first screening for a pilot experiment. So this kind of complexity measure language model. So trying to measure how good the language model. Again, we say the ultimate measure is the word array difficult. Useful measure is test set complexity. So given a language model, you can assign probability to words. Compression algorithm that encodes W bar using minus log 2 P of W bits can be derived. So we can say entropy H of, we'll talk about this concept a little bit later. So entropy H of word of a model of P of Wi given Wi minus n plus 1 over to the current password. So probably the current word given all password. Let's try to compute the entropy of this particular word sequence. It can be approximated. With sufficient long sequence can be approximated 1 divided by the number of words, sum over log 2 of P of W. So some log 2 base of this thing, divided by the number of words give you the entropy of the word sequence. Perplexity measure, perplexity of a language model, is a reciprocal of the geometric average probably assigned to a model to each word in the test set. So that's 2 to the h, due to the entropy of the word sequence. So this test set perplexity evaluates the generalizability capacity of the language model. Training set perplexity evaluates how language model you train fits your data. In the current deep learning notation, we'll call this thing loss, right? So perplexity can be seen as a loss. Looking at training set loss, it tells you how well your model fits your data. Looking at the perplexity, or we call it loss. In your test set, what you can see is how well the trained model fits the test set. Whether there's some mismatch between the two. Hopefully, these two are very similar in a way. So it doesn't. That means that it generalizes well from the training set to the test set. Low perplexity, we call it better ASR. Because perplexity is a measure of complexity. Now it's some kind of 2 to the entropy, right? So again, if you remember what entropy, right? Entropy is something that's high. Entropy, something is high, that means something is variable. There's more variation of something. That's called it high entropy. Less variation, I think that's called less entropy. So 2 to that h of this thing gives you the overall perplexity. So overall variation of your language model. So last time we call it branching factor, right? So how complex your model can progress through a sequence of words. There are many words that could be possible. The perplexity will be very high. The entropy is very large. Because there are so many ways you can go from this word to many words. So that's kind of the notations that we're trying to do here. So mention that in terms of some information theory concept, brings probability into the thing and talks about it in terms of perplexity, complexity, and so on and so forth. So essentially, a statistical weighted word branching measure on the test set. The higher means the more branches recognized you need to consider. A language model perplexity X has roughly the same difficulty as another language model in which every other word can be followed by X different number of words with equal probabilities. You can somewhat equate these two are very similar. If you have a language model, you evaluate the perplexity of that language model. If it's 100, that model equals to assuming you have another language model that have 100 words that can be split every time with equal probability. Okay, so that's why we call it sort of a branching factor. Okay, every time there's 100 different ways you can choose a word with equally likely to move to the next word sequence. Okay, so perplexity is kind of that measure, branching factor, and then so on and so forth. Lower perplexity usually is a better model. Okay, if you have this is Wall Street Journal, 38 million words. If you have 1.5 million words as you're testing, okay, your n-gram order is unigram, n equals 1, your perplexity about 962. So branching factor about 1,000. Okay, every word, it's like you have a language model that have 1,000 words. Every time each word is like equally likely to happen for every frame. Okay, right? That's sort of branching factor at 900 something. Bragg-gram, right? As you start to add more grams into this thing, okay, the perplexity start to decrease. Okay, they're just less way a two words will happen together, right? So there's less branching factor. Okay, when there's less branching factor, then you have perplexity will start to drop. Okay, trigram even lower and lower. Okay, so trigram is usually what people do in terms of ASR. I mean, if you have large amount of data, you can go to 4 gram and 5 gram, but that's only when you have very large amount of data. Otherwise, trigram is usually what people do in the standard ASR. So the more gram you have, the less complexity, less branching factor. That perplexity evaluated as some functions of the entropy on the word sequence. Okay, that entropy is a probability measure on the word sequence. Okay, so keep that in mind. Okay. So again, that was already what we know again from last time. I want to do a little bit segue and talk briefly about information theory, just a little bit. Okay, just to have a concept. Just keep this in mind. Okay, if you're doing an ASR system, reading up papers and what people have done. Okay, when you read up things that talks about language modeling within the ASR or just language modeling generally, okay, there's always a assumed background knowledge of information theory that you know. Okay, so I want to do a brief intro here. Okay, if you want to take an actual course, it'll be good for you. Okay, to actually understand what that is about. Okay, so brief background about information theory. Entropy. Okay, so we talk about entropy. Let's properly define that. Okay, entropy is the amount of information derivable from outcome xi depend on its probability distribution, right? And it's discrete. Okay, so outcome 1, 2, 3, 4, 5. Okay, and then why information theory works well for language, because you assume language is a discrete token. Okay, you have word 1, 2, 3, 4, 5. These are discrete kind of categories, right? So they mentioned the amount of information derived from outcome xi, and each of the word has a probability that generates it, right? So n-gram language model assign probability to each word, or to bywords, or to triwords, right? So there's a probability you can associate with that particular outcome. Okay. So that's the information is information on a particular random variable. Okay, x of I, right? It's the outcome of a random variable. Okay, information theory on that is a log of 1 over p of xi. Okay, it's a log base 2 1 over px2. So if that log has base 2, we call this information is going to be measured in bits. Okay, it's the computer bits, 0 and 1, 0 and 1. Okay, so information on a particular outcome, okay, equals to 1 over the probability of xi. Okay, so again, intuitively, probability of xi, the probability of an outcome, if it's small, okay, then you have a large degree of information because it corresponds to a rare event. Right? It's very nicely formulated, right? Because it's reciprocal. Okay, so you have a probability of a particular outcome. If that probability for ith outcome is very small, okay, 1 over that, okay, take a log, this number will be very large. Okay, so there's a large information when this thing occurs, because that thing is rare. Okay, so we call that this kind of measure is an information measure. Okay, log independent event. Okay, if you have independent events, so you have probability of x1, x2 joint distribution. If they're independent, then what happens? All right, because that joint distribution become product. Okay, and because of the log, then you have these two things acts. Okay, so if you have two independent events, okay, the total information about these two independent events are information about one event plus the information about the other events. Okay, so again, it's a simple exercise, right? Taking log base 2 of the probability distribution. Okay, then you turn the whole framing of probability into information. Okay, so we don't talk about recyclable probability anymore. We talk about information of a random variable. How much information does it have for this event to occur? Okay, if it's large, that means its original probability, how likely it's going to happen is very low. Okay, you have two events, two outcomes, joint distribution. If they're independent events, they factor. Okay, when they factors, then your information about the total thing happens becomes summation. Okay, so again, so keep this in mind. Okay, suppose x is a discrete random variable taking value xy, okay, from a finite or countably finite sample space, right? X equals to x1 or xa, some infinite set refer to an alphabet, right? Imagine these are all possible words that could exist in a particular language. Okay, there are discrete outcomes infinite set. Okay, symbol xi, right, a particular word is produced from the information source of alphabet set S according to the PDF of that random variable x, right? So an important property that we can derive from information source, okay, is the expected information, right? Because now every outcome has an information, okay? That outcome has been generated from the entire source, right? This alphabet source, right? Each outcome is a random variable that generates some that has its own probability. Okay, this entire is an information source. Okay, we want to talk about the average information or the total information that exists in this alphabet source. So important property of information source, we can call that expected information. Average amount of information, we call that entropy, h of x of that random variable x. Right. So this random variable can produce infinitely countable symbol set. Okay, these symbols are just the words. Okay, each one has a probability. Okay, now we want to measure this random variable x on average. How much information does it have? Okay, we call that entropy. Okay, so entropy h of x. Okay, is just the expected value on the information of this entire set. Okay, so what it is basically expected value, right, of these things. So expected value, this basically means sum over all possible things this thing can take, right? And probability of that thing multiplied by the information of this thing, right? So this information has this probability associated to it. This entire source enumerate all the possibility. Okay, that's the expected value. So entropy is the expected value of information on a particular random variable source. Okay. So again, what that is basically sum over all possible symbols, right? P of xi log of 1 minus P of xi. Okay. That equals the expected value of minus log P of x. Okay, so because this this thing. So the average information required to specify the kinds of symbol has occurred on average, right? So again, this is expected value. So entropy, if it's log base 2, okay, it gives you bits. Okay, it tells you average amount of bits, okay, required to specify the number of symbols you have, okay, on average within this set. Okay, you're producing 0, 1, 2, 3, 4, 5, 6, 7, 8, 10. Okay, there are 10 symbols. Okay, each one may have associated probability. Okay, then we can compute the entropy of the information on those 1, 2, 3, 4, 5, 6, 7, 8, and 10. Okay, then you get the number measured in bits. Okay, that gives you the average amount of bits that required to specify what kind of symbol has been produced on average from this source. Okay, so you see how information theory is a very nice tool, a mathematical tool that Shannon develops. Right? Shannon, people know Shannon, right? So the night question in this sense that he develops to bring probability to computers. Okay, so you start to measure things in bits, okay, so that you can process random stuff. Okay, so it bridges that kind of a probability theory into the numerical bits that we're operating in computers. Okay, so in communication, this is a very these are kind of the things that people also do a lot if you're from a communication background. Right? The channel has to encode a certain bits from the receiver to a transmitter and all sort of stuff. So anyway, entropies specify the amount of bits that are required to specify the number of the symbols. So it specifies the average of uncertainty for the simple set. Okay. So these words are interchanging. Okay. Uncertainty and information. Okay. The larger the information usually means the larger the uncertainty. Okay. So that means it also carries a lot more information. Okay. So this intuitive concept, keep in mind. If something is deterministic, okay, this thing will always occur. Okay. Then there's very little information about it because you don't need to know about it because it's going to occur. Okay. So the sun always rises tomorrow. Then deterministic, so there's no information about me telling you the sun is going to rise tomorrow because that doesn't tell you anything more than common sense. Okay, right? So information, if I tell you something that's very highly variable, right? For example, there's a probability that this can be on the final exam, that cannot be on the final exam. That information is going to be larger, right? Because it's uncertain. Okay, there's a lot more information you want to actually get from this kind of knowledge. Okay, so information associated usually with uncertainty. Okay, the larger the uncertainty, the larger the information. Deterministic gives you zero information. Okay, so we have to keep that in mind in terms of probability, understanding what information is, understanding what entropy and is. Okay. So we know entropy, it obtains maximum. Okay, at what point, and when the PDF is uniform. Okay, when all outcomes are equally likely. Okay. There's the most uncertain, right? Because every possible thing can happen with equal likelihood. Okay, so there's no one thing that's more likely to happen than the other thing. Okay, then your PDF is uniform. Okay, then your entropy is going to be maximum because your uncertainty is maximum. Because no outcome is more likely to occur than the other outcome. So for any PDF to make the entropy the largest, okay. You just assign the uniform distribution, okay, to the thing. Okay. And again, always keep thinking in terms of language model, right? When we train language model, okay, there is a underlying boundary hypothesis that not every word is equally likely to happen. So you want to find a language model that encodes that probability in a way that try to have lower perplexity because the perplexity is an entropy measure on the word sequence, right? So again, entropy measurement is an expected uncertainty. So you want to have the expected uncertainty to be as small as possible when you have a language model. Okay, so that means you're really trying to learn how some words are more likely, some words are less likely. So you want to find a language model that way. But anyways, come back to entropy. So entropy is always positive. Okay, there's no negative entropy. Okay, with equality equal to 0 if a p of x1 equals 1 or for some xi, right? So entropy can only be 0 when there's a deterministic output. Okay, when one of the outcome is for sure it's going to occur. Okay, then there's no entropy. Okay, so on average, the expected information is 0. Okay, so there's nothing more. Okay, you always know that thing will occur. All right, so now let's think about another thing. Okay, if the probability function of a generating symbol xi is some other probability function q instead of our guess p. Okay. Right, so for example, now we say, okay, x is a random variable. Okay, p of x tells me the probability that's generating this random variable x. Okay, what if my guess is wrong? Okay, what if the way I assign p of x is wrong? It should be q, okay, not p. Okay, now the new entropy, okay, is going to be no smaller than the original entropy. Okay, we call this Jensen's inequality. Okay, so h of x equals the expected value of minus log p of x. Okay, this entropy is always less than equal to log of q of x. Okay, so if probability function of generating symbol is some other q function instead of our guess function, okay, the entropy is always going to be large. So if we misestimate distribution governing the data source, okay, we again become more uncertain about the data. Okay, so it can be easily proved. Okay, minus f of x log f of x is less than equal to minus g of x log f of x, right? So if this PDF, right, is the correct PDF, okay, so we take integrating over the entire sample space, the function, the probability function, the log of that function, okay, this expected value is going to be less than log of this PDF function when we multiply by some other function, okay, with equality only occur when f of x equals to g of x. Okay. In this thing, so when we say, okay, let's say log of x, we know it's always less than equal to x minus 1. So summation of SP of xi log of q x of I divided by p of xi is always less than or equal to sum over all SP of xi, q of xi, p of xi minus 1. Okay, then this thing equals to 0. So we know on the when you misestimate the probability distribution function, your entropy is going to be larger. Okay. So from this, you can define what we call a Kullback-Leibler divergence distance. Okay, between any two distribution function. Okay, KL divergence. Okay, KL divergence between two distribution. Okay, that's the expected value of log of p of x divided by q of x. Okay, so again, that's sum of SP of xi log of p of xi q of xi. Okay. We often also call this relative entropy. Okay, also we call it discrimination, we call it divergence, and so on and so forth. Okay, and then if people here have run some deep learning, right, KL divergence is a loss that you also use it to try to train your system, because it's a information theory based measure to measure the similarity or dissimilarity between two distribution, okay, two probability distribution. Okay, if you want to make sure this two probability distribution matches, okay, you want to minimize this KL divergence. Okay, so that's why this kind of KL divergence can be seen as a loss function. Okay, when people are trying to do deep learning optimization, but that originally come from the whole information theory, talking about symbols, language model, and so on and so forth. Okay, anyway, so keep all this in mind. Okay, perplexity of the source. Okay, basically is 2 of h of x. So average choice for an alphabet, and then describe how confusing the language of the model is. Okay, we'll continue with some more of this, just to keep this thing fresh. Okay, the reason why we teach this, because if you, like I said, if you read ASR papers, if you talk about language model within ASR, there's always a notion that people realize you have to know this kind of stuff. Although these are not coming from a speech course, it's supposed to come from an information theory course. But these are important fundamental concepts. Conditional entropy. Okay, consider transmission of symbols through some information channel. Right, X is a set of input alphabet. Y is the output alphabet. Okay. Mij is the probability of yj given xj, which we call the conditional probability of receiving yj when xi was sent. Okay, this Mij we often also call this channel matrix. Okay, so if you're coming from a communication background, it should be very straightforward. This input, right? This is transmitting side, receiving side, the channel. Source is p of x, right? X channel p of y given x, then you receive y. Okay. Prior to transmission, right, the average amount of information or average amount of uncertainty, okay, of the input alphabet, we call it prior entropy. H of x, right? This is a source. These are a set of symbols I'm going to send. These are a set of languages, a set of words I want to send. H of x equals sum of k x p of x equals xi. Log 1 over x equals xi. This is called a prior entropy. Okay, after transmission, say yi is received. Okay, right. So the average amount of information on the receiving of the input alphabet is reduced to the following distribution, posterior distribution. Right. The entropy evaluated on the x, the original input. Now I know y takes on the value of y. Okay, because I received yi, yj. Right. So yeah. So to evaluate this is sum over all possible xp of x given xi when y has been received, right, times the function, which is the log of the probability, right? This is information, a log of probability p of x given xi and y given y equals to yj. Okay. All right. So this is entropy of x when y I receive yj. Okay. So we can extend this to say, okay, let's find the average of this thing out, because this is only when y receives y, right? At the output, okay, when the particular y has received, and look at the entropy, okay, of the x. Okay. So we can also look at that average over all y, right, over all possible y's I can receive at the receiving end. Okay. So h of x given y, okay, that equals to h of x given y equals yj, sum over all possible y that you can take. Okay. Also then times the probability of y takes on a particular yj. Okay. Then gives you the average and the entropy of x given y, these two random variables. Okay. Okay. And then you can just expand this. Sum over all y's p of y given yj. Sum over all x p of x given xi y equals yj log p of xj given y equals yj. And just put it together. Sum over x, sum over y, p of x takes on the value, y takes on the value, log of probability of x takes on the value, given y takes on a particular value. Okay, so they give you h of x given y. Okay, similarly, we can also define the entropy between input and output together. Okay, so joint entropy between two random variables. Okay, that's minus sum over x, sum over y, probability of x given xi, y given yj, log of p of x given x is xi, and y equals to yj. Okay. Then you can massage your term, okay, because this joint distribution can be factors into this plus this thing, right? Probability of joint equals to prior multiplied by conditional, right? And then you insert a log in, so this prior multiplied by the conditional now becomes a summation. Okay, so sum over all x, sum over all y, p of x given xi, y given yj, log of this thing plus log of this thing. Okay, this multiplied by this and this multiplied by this. Okay, this is just h of x. Okay, this is just h of y given x. Okay, so the joint entropy, okay, between x and y, input and output, alphabet source, okay, on the receiving side and the transmitting side equals to the entropy, the total, right, information, total average information already exists in the source, plus the conditional entropy, okay, that when the source is dead, what's the output that we receive, okay. So the uncertainty about two random variables is the sum of certainty about one random variable and the conditional entropy of the second, given the first one is known. Okay, so this chain rule, okay, for entropy can be developed. So entropy for an entire sequence or entire joint random variables equals to h of xn given xn minus 1 plus all the way back x of x2 given x1 plus h of x1. Okay, so h of x given y and z, when you're conditioning on more variables, is always less than equal to h of x given y. Okay, so uncertainty decreases with more information. And what happens when this thing equals? Okay, when your z is independent of the other events, okay, then these two entropy will equal to each other. Okay, so I'm not sure if you start to get a sense here. So the information theory, okay, the way of looking at entropy, information, all these things, conditional entropy, covalent divergence, all these things, it has no new math. Okay, this split is based on probability. What happens is you insert the log, okay, and you change the name, right? We already have a probability chain rule. We already know joint distribution factors into conditional probability multiplied by by less and less of condition. Okay, so we already have that chain rule of probability. And now we have a chain rule of entropy. Okay, instead of multiplying, you have a summation. Okay, so the only thing that has changed is all the information theory problem. They take a log into the entire process. When they take a log into the entire process, a lot of things become summation and all things. And then because they're log base 2, okay, because of log base 2, there are a lot of the unit they can measure things become bits. Okay, so then we can use this kind of concept of understanding discrete outcome, discrete events we want to encode using our computers to be able to process them as discrete events, discrete things. Then you can basically base off, okay, the information theory map that tells us what to do. Okay, so take this in mind. Okay, when I first learned information theory, I find it very odd because look at the details of the derivation. There's no new math. Okay, it's all the probability operation that you've already been taught as probability class in your undergrad. Okay, but information theory is usually is a graduate course, okay, but there's no new math. Okay, it's inserting log and rephrase everything into information, bits, entropy, uncertainty, and all those stuff. So you don't talk about probability anymore. You talk about average information, talk about uncertainty. You talk about the number of bits I need to require to encode the entire space. Okay, I talk about the number of bits I can send it through a channel, okay, to make sure my entropy is maintained or reduced. So those kind of stuff. Okay. So again, there's a theorem around this, Shannon's source coding theorem. Okay, a source cannot be coded by fewer bits than its entropy. Okay, so entropy provides the upper bound for a source loss decompression. Okay, so again, if you're doing compression, right? So on your things that you want to send, okay, you cannot encode that source by fewer bits than its entropy, because entropy tells you on average how much uncertainty about the thing, right? So if everything is equally likely, so if you have 100, say you have 32, if you have 32 words you wanna send, right? So that's 4 bits, no 5 bits, right? So if you have 32 events that are equally likely to occur, okay, then then the entropy, okay, will be 5, okay, because that it requires at least 5 bits, okay, because everything is equally likely. So all of these are just 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, okay, 0, 0, 0, 0, 1. So there's no compression algorithms you can do to compress the sending of zeros and one, okay, to the other side, so that it's a more efficient transfer, because every item is equally likely to occur. So all the things are orthogonal, okay, all the entropies are orthogonal, so those things need to be added up. So you cannot code less than that number of bits. So in terms of language model, that's essentially what people are trying. You're essentially compressing the language, right? So if you have English that have 10,000 words, okay, if every word is equally likely, then you need 10,000 bits, okay, to be able to encode that entire process. But no, usually what people do is say, okay, I learned a language model, so I know the probability, okay, of each word likely to occur or not, okay, and I can compute the total entropy, and I know the minimum requirement of the bits I can use to encode they can design algorithm to actually encode this set of language, this set of words. So two things. So again, language model plays a role in that kind of context. Okay, so intuitively, entropy increases, uncertainty increases, amount of information increases, therefore you need more bits to encoding of the information. Okay. Another concept called mutual information. Okay, the shared information between two random variables. That equals what? That equals the entropy of the random variable minus the entropy of the random variable when I know u, right? So x given y. Okay, so when by having x given y, and if y has a lot of information about x, okay, then this number will be small, okay, because this becomes very deterministic. Okay, so if y has a lot of information, when I know y, when I know you, when I know your name, I know you, right? Then if his name is you, okay, then if I know your name, then I know you, okay, this entropy will be very small. There's very small uncertainty. Then there's a lot of mutual information. Okay, there's a lot of information that's shared between these two sources. Okay, when I know you, but it still doesn't make my entropy much smaller. Okay, then the mutual information will be very small. Okay, that means by knowing y, it doesn't help me reduce the entropy of x. Okay, then the mutual information between these two random variables can be very small. Okay, so mutual information is the average amount of information provided by the random event y about the random event x. Okay, average difference, number of bits, okay, it takes to specify the outcome of x when the outcome of y is not known and the outcome of y is known. Okay, so the difference between when I don't know y and when I know y, okay, the average number of bits difference required when I know y and when I don't know y. Okay, that bit we call that, okay, mutual information between two random variables. Okay, you can explain that. Okay, if you look at the math, it's nothing more than you have inserted some log here. Okay, so the mutual information is just this is the h of x, right? This is h of x given y. Okay, so we can put it together. So sum over x, sum over y, p of x, y, log p of xi given yj, p of xi. Then you sort of collect the terms, so it becomes basically the expected value of log of p of x and y joint distribution divided by p of x and p of y. Okay, so again, if you like look at it from a probability sense, it's pretty easy. Joint distribution between two random variables divided by the marginal distribution of x and marginal distribution of y. Okay, if they are very if they are very independent, this thing will goes to again 1. Okay, the log of that will goes to 0, very small. Okay, so when they're very different, the log will have some value, the expected value will have some value. Okay, so then that becomes the mutual information. So the mutual information between x and y, they are symmetric. Mutual information between x and y is the same thing as mutual information between y and x. Okay, p of x, y, p of x, p of y is the mutual information between symbol x and y. Okay, mutual information is always sitting between 0 to the minimum of the entropy of x or y. Okay, so you cannot get more information out of the original information source. Okay, the largest information source exists in the original set, the original source. Okay, by knowing each other, you basically only know the shared portion between two random variables. Okay, so that always has to be between 0 and the minimum of the source. Okay, and we call noise this channel is h of x given y equals to 0. Okay, channel capacity. Okay, you might have heard about this thing. The channel capacity is max over px of the mutual information between x and y. Okay, so out of all distribution of x, what's the maximum mutual information between x and y? We call that C, and we call that channel capacity. How much sort of stuff you can send over, say over the air, okay, over the length line. Okay, the capacity also measured in bits, right? Because these are all mutual information. The mutual information between the receiving side and the receiver side, maximizing overall probability distribution. They give me the maximum capacity of the channel. Okay, how much information I can send from one end of the source to the one end of the receiving side. Okay, without any distortion. So repeat, so this is what I of xy is measured information at y carry about x. Okay. All right, back to LM. Okay, so again, that was a very quick sort of intro to the information theory. So when you look at entropy, mutual information, okay, all these terms, when you read up language model perplexity, right? Perplexity defined as a function on the entropy. All those things are coming from information theory. Information theory is coming from the probability theory. Okay, by again repeat, I said it basically adds a log-based thing into the whole, into everything that you know about probability. And because of that log-based 2, okay, it starts to talk everything in bits. When you talk about everything in bits, then you have a way to operationally do that in computers. Okay, you imagine, okay, what's the buffer? Okay, how many zeros and ones I can send? Okay, how do I send it over a channel? Okay, what's the capacity I can send over a channel? When I'm at the receiving side, what do I do? Okay, to make sure that thing will be reduced. Okay, in terms of LM, right, people use this kind of terminology because language model is by definition a fixed symbol set, right? So the most classical use is back in the days where they transmitted like Morse code, right? So when you try to do in military, when you send the code, right? The way you design the coding of a particular word by tapping, 3 times here and 3 times there, and 1 time here, 1 time there. That particular tapping is a coding, right? That coding depends on the probability distribution of the word that you frequently use in military, and use it to do transmission of the code. Okay, so that was the process, and then that kind of terminology started brings into the language model. And the language model effectively, think about it, is trying to estimate the probability distribution of a symbol set, okay? To make sure I know which word or which sequence of words are more likely to occur after the other sequence of words. So the goal is to minimize the uncertainty about my branch. So the perplexity is a measure about uncertainty, okay? Some average amount of uncertainty about an alphabet set. So if I have a language model, if I compare to language model, the one that have a lower perplexity, that means it has on average a lower entropy over the entire entropy set for that language. Okay, so that means that model probably captures this kind of the distribution of the language a bit better than the other model. Okay, so that concept coming from this thing. Okay, again, repeat. So last time I think we talked about the CAD smoothing. So again, CAD smoothing, just keep in mind. Okay, it works all the way into almost 2000. Okay, things have developed after CAD smoothing in terms of purely language model. It probably improves, the language model generally by only 1 or 2%. Okay, so the large amount of improvement really come from the idea of combining good Turing estimate and back-off model. Okay, these two things together to be able to help us do, say, trigram language model learning with CAD smoothing. So you combine good Turing estimate by adding the combinations of higher order model with lower order model. So when you have enough votes, enough counts, okay, for a particular bygram count, okay, you just use that count. Okay. If not, you back off to the unigram, but with a certain weighting factor that depends on the previous word. Right? So we call this DR, the discounting ratio. Okay. The number of votes, okay, that you grab from those counts that have non-zero votes and then distribute it to this thing. Okay, they need to be well distributed. Okay, so counts subtracted from non-zero counts are distributed among zero counts bygram according to the next lower order n-gram. In this case is the unigram. So how do we choose this alpha wi minus 1? So we want to choose it such that it could equalize the total number of counts in the distribution. Okay. So this is the new counts of the WIC star wi minus 1 wi. It has to be equal to the original WIC of wi minus 1. So this alpha of wi minus 1 is first 1 minus all the original counts that has more than 0 counts, their new count probability divided by all the original counts that has only 0 counts, the probability of the unigram probability. So again, taking the ratio between the two, it gives you a weighting factor on how much weight you give it to the unigram probability when you back off from the bygram probability to the unigram probability. Again, you can rewrite this, but that's just 1 minus the W, where it has non-zero count, this probability by the 1 minus the ones that have non-zero count, the unigram probability. So, and we know this P of star of WI divided by wi minus 1 is the new count of wi minus 1 wi sum over the original word set, the new count of wi minus 1 wk. Okay, so how do we choose dr? Okay, dr equals to 1, okay, for some r is greater than k. So that means you don't do any discount for the bygrams that have large amount of counts, okay. For dr, this when k is usually above 5 to or above 8, usually don't discount any more of those bygrams. Okay, less than that, before it hits zeros, the range of the counts are the ones that are being discounted further, and those are discounted further are going to be distributed to the 0 count bygram by looking at the unigram probability with that weighting factor of alpha that was computed in the previous slide. Okay. So discount ratio for R less than or equal to K is calculated from good Turing estimate applying to global model distribution. Okay, and the number of bygram occurring R times in the training data set. So dr is some again another ratio of R star divided by R for R from 1 to K. These counts are proportional to those predicted by the good Turing estimate. So good Turing estimate is basically you reshuffle it between using 1 count for 0 count, 2 counts for 1 count, 3 counts for 2 count, and then 4 counts for 3 counts. And when you hit a threshold of k counts, then you stop doing the good Turing estimate. Okay. All right. So that was language model. I want to do a final recap on the ASR. So again, the whole business about language model is because we started to talk about connected word recognition. Okay. So repeat it back. Okay. This course is really about automatic speech recognition from the beginning to the end. Okay, so everything we teach is actually centered around how do you build a automatic speech recognition system. Okay, so it starts by looking at a feature parameterization. Okay, that's where we treat signals as signal. Okay, we understand the signal's time frequency properties. Okay, we bring the concept of speech production. Okay, source and filter. That's why we design the male filter bank, and then followed by capsular analysis so that we derive the MFCC. Those are speech representation, representing that one-dimensional signal into a set of features. Okay. Those set of features supposedly tease apart the source and filter, whether the filter really captures the way we speak. Okay, so those are the features that remains. You have this sequence of features. You want to map to what? You want to map to another sequence of symbols. Okay, that's the speech recognition part. Okay, so the speech recognition part, again, we separate into two parts. Okay, one is called acoustic model. Okay, so because from the features to the actual written text. Okay, there's an intermediate layer because the way we listen to the sound, there's a phonetic transcription. So you need a dictionary that tells you every word and how it's being pronounced. When that basic unit, we call it phoneme units. Okay, so we are essentially trying to map the features, a sequence of acoustic feature to a sequence of phoneme symbols. Okay, that phoneme symbol is gonna turn them into word because you have a dictionary. Okay, then that kind of process is called the entire ASR process, taking a sequence of acoustic feature into a sequence of a written text. Okay, so this is very specific. Okay, so understand ASR is meant for taking what we hear in sound to what we write. Okay, on paper. Okay, so not to write what we hear. Okay, it's write what we would do it on paper. Okay, so that's the written language. Okay, from spoken signal. Okay, so ASR is taking this component of spoken signal into a written symbol. Okay, like how we human are doing things. Okay, the acoustic model give us a representation on phonemes, basically descriptions of the way it sounds, the pronunciation. Okay, so turn the features, try to map into a set of the phoneme symbols. Okay, now HMN just help us to learn that because the problem is every phoneme, every person say it a little bit differently. Okay, so the MFCC can be different. So you want a Gaussian model that every person say with a different duration. Okay, so you want to have a flexibility in terms of the temporal components. So you have HMN trying to model that entire process. Okay, once you have this, right, you have acoustic signal, acoustic model, you can train it and then do phoneme classification. Okay, but in terms of connected word recognition, probably not because you have a connected set of phonetic symbols. Okay, and eventually become a connected sequence of words. Okay, so P, you have W set of words and drawn from the size of NV given the others is O1 to OT. You wish to find a word sequence and maximize the probability of observation, right? At each time, you have a possible word candidate you have to choose. Okay, you essentially again look through all the word candidate, all their state. Okay, and look at every frame which word is most likely. Keep that in knowing that if I'm the most likely word at this particular time, where did I come from? I come from maybe one of the previous words, some other state, the same word, but that gives me a large likelihood. Or I have come from the other word, okay, jump into this word. Okay, so there are two ways every frame, every word, okay, can be most probable, right? It could be switching from other to this, or it could be staying in the same at this, and you keep that into your memory and then try to do all those things, right? So you find a most likely word sequence, okay, and the most likely word sequence probability is this, okay, to solve this sort of argmax problem. Okay, so in repeat, these are MFCC frames. Each frame, there's a potential word, okay, state that you want to keep your vector-B decoding, okay, right? So imagine this vector-B decoding that you've done in HMN is the same thing that you've done in the word sequence, okay? You've tried to find the most probable word state transition, right? So assuming each word is a state, okay? So you want to find that most probable word sequences, okay? Of course, it will get complicated because every word is composite of a 3-state or 5-state HMM. So every frame we need to unroll the HMM first, and then once you unroll it and look at within each word's HMM, and then sum of those probability to become the probability of that particular word. So that's the only thing that's different here. So you need to, again, you have to still unroll HMM, right? So for this word, under this word, this particular model for this time, okay? So this word, we're assuming that word, okay, is a phoneme word, okay? Each phoneme has a particular state. I can go from 1 to 3 or 1 to 5 based on HMM state you have at this particular time, okay? Again, you're unrolling the word, okay? And also you'll find the maximum probability, okay, of these things, right? So basically you sum over possible states of this unrolled alpha variable, okay, at each time, and sum of all the states, okay, for that particular word you have. So to give this probability. Now we need to find every frame you unroll it, compute this probability, and we need to find max over all past. What's the largest probability that we keep it here? So we want to find that max probability at the end. Okay, so that max probability can have let's switch the max probability can have two forms, right? Every time is either the word maintains the same word as your previous time, or the word that is not the same as previous time, right? So every time we want to select, okay, keep whatever that model keep the criteria, keep which probability and which of this is most likely, right? So we want to keep it for every time. Unroll the state, look through the weight of these words, okay. Then for every word you do the same thing, then you unroll to the next time using the alpha variable, then you sum up all the states within that word, and then you look at those words, whether it has to be the same word or have coming from the other word, keep which one is the largest, keep the index where it have come from, for all the words, all the states, okay, unroll it, and then do the next time, until you hit the end of the analysis, okay, you'll find which word is largest, okay. Look within that word, okay, either I have come from the same word, or I have switched from the other word, and I also know which word I have switched from. If I know I have stayed the same word, I'll just go back one time frame. I keep looking into that frame and say, okay, if I'm the same word, within that same word, am I the one previous is coming from the same word, or I have switched, right? If I have switched, then I will go to the switched one. Okay. Then we look into the switched one, and I say, okay, am I staying the same word where I come from, or I have switched from the other word? Okay, so you kind of this backtrack. Eventually, you get a best word sequence model. Okay, so the decoding of the word sequence is the same decoding as the HMN single HMN state sequence. It's just that every time you have some of those states, okay, within each word. The rest of the decoding is just Viterbi decoding, right? So it's decoding. Okay. So expand that, okay. Because this is a summation of these things, right? So this, the probability of if you are not coming from the same word, it would happen from when you are in the first state, right, of this current word, okay. The max over all possible other words, okay. Their last state, okay, given their word, okay, times the probability of your current word coming from their word, right? So this probably will compete with this one to see which one is the largest, okay, to keep it for that particular time, okay, to know which word index that is to keep, okay. So, and this particular notation is only because, like I said, the HMM for ASR has a particular ontology, okay. We always go forward, okay. You start at one, you end at the last state, and then only when you end at the last state, you will switch to other people. Otherwise, you'll maintain your HMN. Okay, so you look at this NWQ, that means the other words has reached their last state. Okay, given that's the other word. So the other word has reached their last state. Okay, out of all possible other words, okay, their words have reached the last state. And then if I am this particular word and you are that particular word, okay, what's the probability of you coming to me? Okay, and this is the language model. Okay, that's the language model. This is the HMN decoding. This is the HMN decoding within word. Okay, this is the HMN decoding connection between different words. Okay, then this probability is the language probability. Language model, we call it word string probability. Usually you can obtain from the language model. So whatever language model you do, okay, you can insert it here. Okay, or if you don't know anything about language, you said every word equally likely, okay, then that's basically tells people you don't know this word probably there's no language model within your ASR system. You just set every word equally likely to connect to other words. Okay. Or if you have a language model, basically this is where you insert the language model. And then once this insert language model, the entire thing is a Viterbi decoding from the beginning to the end, where you hit finally the end and you backtrace all those things and get the final get a final word sequence, right? So again, we put all these things together, you have compute the probability at this time of which word, okay, it records the maximum, okay. You have another variables, we call it address, okay, it tells your route to say, okay, when at this time, at this word, which one of this is the largest, I'll keep that index, okay. So when I'm in here, for all the words, I'll look at the PA, okay, look at which one is the largest, I look at, say, V1 is largest, okay, the V1 is largest, I'll look at the V1 at this time, the index, is this staying in the same word, okay, for the previous time, or I have switched from other words. If this is largest, I'll just go here, and I know which word that is, I'll go look at that PA, okay, within that, look at their address, if I stay in the same word, or I have switched another word, and repeat this entire bi-turbidity decoding. So, no bi-turbidity decoding by heart, it's very, very important methodology in terms of speech recognition, okay, both training and inference, okay, so it's very at the fundamental core of doing this kind of modern state HMM based recognition system. So I would recommend you to really go deep into it. You should be able to do it by hand, like we're doing the example, okay, do it by hand to do an actual bi-turbidity decoding, okay, think about the problem in just coin tossing. Trying to estimate the possible state, possible coin, right, possible flips, okay, and backtrack. So again, know that kind of process, because bi-turbidity decoding is very, very important in this continuous word recognition kind of process. Okay, so termination and you backtrack and you get the final state probability. That concludes the entire modern state ASR system on statistical base. Of course, there are many tricks we didn't teach, okay, but this gives you the backbone, okay? There are many tricks that people have played, okay? Not just, learning the MLE estimate, okay? They will add more discriminative laws, okay? There are people that will put together not just a single phone, okay? Multiple phones, we call it diphone, triphone, put them together as a single HMM, okay? So not just one phoneme for one HMM, okay? You have triphone, okay, as an HMM. So again, this combination can be a lot, right? Because if you have 42 phonemes, right, then you have 42 basic combinatorics, okay? Number of possible ways you put together 3 phoneme set, okay? That becomes one triphone. When you become that many phonemes, then you don't have enough data, and then people play some tricks to make sure I have enough data for each triphone, okay, to be able to do my HMM. So many tricks that people have developed over, the past 20 years. To improve the modern state HMM, but I think generally, if you get a very good understanding of this bi-turbidity decoding HMM GMM structure, MFCC, okay, this paves the most basic workable system, okay, for ASR. And then for the deep learning thing, okay, I can tell you is we'll talk a little bit about that. The first version of deep learning doesn't change anything about the structure. What they change is this probability only, B of I, V of T. Okay, that's the only thing. Okay, instead of saying this, right, is saying, okay, this at a particular state for that word, okay, I have a Gaussian mixture model. Okay, so I can give you a probability of that P of state given the observational sequence, P of Q given observational sequence, right? So we can this probability is being re-estimated. Okay, instead of using Gaussian mixture model, use say deep neural network. Okay, where the output layers are basically a multi softmax over in different state. Okay, so it gives you a probability weighting on the state. Okay, so then you can swap this thing to a deep learning model. Okay, and keep the rest of the entire structure similar, okay, to the HMM GMM model. So the only thing will be switched out, okay, is the GMM. Okay, that you can use DNN to train that probability P of basically this BIV, right? For each of the state for that particular word, when I see this observation, what's the probability? Okay, so I can compute this probability using a DNN, okay, because that essentially is a classification problem, right? When I see this observation, what's the probability of me seeing this state? It becomes a classification problem, right? The probability of me seeing observation so that it goes to state 1 or state 2 or state 3. Okay, that's a standard, okay, deep learning, n-class classification problem. Okay, if you switch that out to deep learning, then this can be estimated with the deep learning probability. We'll talk about a few things there, and then in fact, the Kelly, if the TA asks you to run all the way to the deep neural network, that's only thing that's been changed. This thing, it changes the way this the output probability has been estimated by other things. Okay, then the modern right, the very large scale ASR system, like I said, is essentially eventually they will combine everything together. There's no separate acoustic model, no separate language model. There is no need of a dictionary, okay, to map all these things. Okay, basically they learn directly from the signal to the written text. And the written text they become a character, so they will take every frame in, and then output is a certain character. Okay, so CAT. So they don't rewrite as cat as a phonetic transcription. They just write cat as CAT. Okay, and I take the signal map into CAT. Okay, so that's the end-to-end. Get rid of dictionary. Get rid of the language model. Okay, taking the acoustic model to directly the character. That's called end-to-end. But the entire structure still very similar. Okay, so but I want to say, okay, understanding this entire pipeline is important for understanding the modern state ASR, because they all build upon this. And I think just 2014, 2015, that's when ASR community started to switch it up, this probability to DNN. Okay, that's only time where actually deep neural network has been started realistically integrated into the automatic speech recognition system. And then people start to play a lot more, okay, with various blocks of these ASR to make sure it works. So it's entire sort of large set building blocks understanding this of every single item of this thing. So again, repeat, okay. The course will, and I think I'll call it off today. Okay, the next time we'll cover new things, more of an overview. Okay, but the actual course stops today. So anything you would expect to be on test will be everything before today. Okay, so what I want to say is throughout this course, to fully get an ASR system knowing well, okay, it starts right from signal system, okay, DSP, okay, all this signal analysis, okay, time series, okay, frequency transform, okay, windowing, okay, all these things are very classic signal system of DSP framework. Okay, the second half is say, okay, now let's get data, right? Now once we get data, and then let's say, okay, let's do a statistical or data-driven approaches. Okay, and then where all this modeling that comes in, where to learn the model like we do it now, training and those things. Okay, and because of the nature of the sequence to sequence matching. Okay, so we have a Viterbi decoding HMM-based thing to try to decode a set of acoustic signal to a set of symbolic words. Okay, that basic structures of Viterbi decoding. The intermediate is HMM plus a Gaussian mixture model, trying to model the variability of the sound. Okay, because it could come from different people, so the MFCC are different. It could be everybody speaks slow and fast a bit differently, so you'll have different durational models. All this thing put together and combine the knowledge of that particular language and then put it in. And every step of this way, you see, we need no probability, no statistics, you kind of need no machine learning. Okay, in language, you kind of need to know information theory a little bit. Okay, you need to know signal system up front, right? So you also need a little bit of science behind the speech production. You need to know a little science about the speech perception. Okay, and later there are a few things we didn't touch today. Is the search. Okay, the Viterbi decoding is okay. But that search space, if you have, say, 10,000 words, each word has 3 different states. So imagine when the compute is probably going to be very slow. Okay, so how do we speed up this search? Okay, there's things we didn't talk about today. So there's actually also more of a traditional computer science, right? How do I do search really fast? Okay, those kind of approaches. I make sure I don't just do Viterbi decoding. They turn it into a more easily searchable graph, so that's why the Kelly is really fast. Okay, because it's not doing a straightforward search. Okay, it's doing a very optimized search. So if you're interested in that, you have to look at courses in optimization. okay, search algorithms, all those things. Okay, those knowledge are also into the space of ASR to make sure those things are also fast enough to be able to do things. Okay, so imagine if you take this course, hopefully it sparks your sort of interest. I don't know, maybe okay, to look back on fundamental math course that that you may have once taken at some point. Okay, but this technology really brings every aspect of this math course into a single technology. Okay, so that to do one simple stuff, making an acoustic sound into a set of symbolic text token. Basically, that's it. Okay, so okay, keep that in mind, and then we'll do lab next week, okay, and then the final exam the week after. I'll do a little bit of a newer state of the art on a Thursday. 好，今天先这样。